Hello everyone and welcome back to our videos. Today we will talk about the continuous loop detector, and this the last type of visual detection system. The continuous loop detection, in addition to the thermoswitch detection system, visual also produces a continuous loop type system that consists of a single fire or overheat sensing element that varies in length depending on the size of the fire zone. A typical sensing element can be anywhere from 1 foot to 15 feet long. As mentioned earlier, the sensing element used in a continuous loop fire detection system consists of flexible small diameter inconel tube. This figure talks about the continuous loop detection and its visual type. It consists of conductor or center conductor, inconel tube, and ceramic with beads covered with iotatic salt. In the visual type system, the metal inconel tube uses a single wire electrode made with pure nickel. This is our electrode that made from the pure nickel. The pure nickel electrode is surrounded by ceramic beads. Here we have our ceramic beads. Why? To prevent the electrode and conductor from touching each other. It will prevent the conductor from touching the inconel tube. The beads in this system are wetted with iotatic salt, which has an electrical resistance that varies with temperature. The center conductor protrudes out each end of the inconel tube, where an electric terminal is affixed to the electrode. Current is then applied into the conductor, while the outer tube, the inconel tube, is grounded to the aircraft structure. At normal temperature, the iotatic salt core material prevents electric current from flowing between the center electrode or the center conductor and the tube. However, when a fire or overheat condition occurs, the core resistance drops and current flow between the center conductor and the ground, energizing the alarm system. As we see here, we have a continuous loop, and I will repeat its component. It consists of a stainless steel tube, and here we have the electrode, and here we have the temperature sensitive material, or what we said, it's the beads that made of ceramic and covered with iotatic salts. As we see here, we have three gauges: the temperature gauge, the resistance of the inside materials, and here we have the currents of the electrode, and here we have the warning light on the cockpit. When the fire exists or an overheat, the temperature will increase. While increasing of the temperature, the resistance of iotatic salt will decrease. When it decreases, it will move the current from the electrode and the out conductor, and this will increase the current and will make a warning light on the cockpit. And when the temperature decreases, we will say the resistance will increase of the inside material and the current will not move. That will make the warning disappear, as we see. We see here a turbine engine and it's connected with continuous loop, but here we have a double loop. This double loop will connect it to a logic gate and it's called AND gate. That for make the false warning not existed. When the alarming or when the electrical current flow from the loop B and from the loop A, the logic gate will open and will make output signals. These output signals will go to the cockpit to make alarming by lights and audible. But if there is a fault in one of them, as we see here, we have a fault on the loop B, and this make a short circuit. When this short circuit exists, they will not move, or the electrical that will go, it will come from one loop just, and this will prevent the gauge for send signals for make fires. When this happens, it will goes to OR gates. The OR gate will move from one of them just. So if the current that come from the loop B to the OR gauge, the OR gauge will make a signals. These signals will go to the cockpit for make a volt. That means we have a volt on the system, not fire. Also, if we have a volt on short A in the loop A or a short circuit, it will give a signals to AND gate and it will not have output because it comes from just one loop. But it will go to the OR gates and the OR gates will give alarming or signals to the cockpit to say that we have a fault on the system. The second type of fire detection system is the KID system. The KID system is also continuous loop type system, consisting of a signal overheat sensing element that varies in length. The sensing element consists of a rigid pre-shaped inconal tube with two internal wire conductors. That means it's the same of the continuous loop in the visual, but here we have two conductors, and in the continuous loop of the visual we have just one conductor. The conductors are embedded in the thermistor or thermal resistor material to prevent the two electrodes from touching each other and the exterior casing. This thermistor material is like the iotatic salts in the visual continuous loop detection. So he say here, like the iotatic salt used in the visual system, the thermistor material has an electrical resistance that decreases as temperature increases. So the function, it will be the same of the visual, but here we have two conductors, but in the visual we have just one conductor with the exterior casing. The third type we have is Lindeberg system. This Lindeberg system called pneumatic continuous loop type system. Why? Because we have an inert gas inside the tube. How this element works? We have a stainless steel housing case, and after that we have an inert gas inside this tube. This inert gas or the tube will connect to a diaphragm switch, or we can call this a discrete material. When this loop is exposed to heat, it will transfer the heat from the stainless steel to gases that inside this tube. The inert gas will expand. This expand will push the diaphragm switch and will connect the circuits and will let the electrical current moves from these circuits and make alarming on the cockpit there is a fire. Here we will read. The Lindeberg fire detection system is a pneumatic continuous loop type system. Why? Because we have an inert gas inside this tube, consisting of stainless steel tube as we see here, filled with an inert gas and a discrete material that is capable of absorbing a portion of gas. The amount of gas the material can absorb varies with temperature. One end of the tube is connected to a pneumatic pressure switch called responder, which consists of a diaphragm and set of contacts. When the temperature surrounding the sensing element rises because of a fire or overheat condition, the discrete material within the tube also heats up and releases absorbed gas. As the gas is released, the gas pressure within the tube increases and mechanically actuates the diaphragm switch in the responder unit. Once the diaphragm switch closes, the warning light illuminates and the alarm bell sounds. Because the Lindeberg system works on principle of gas pressure, it's sometimes referred as a pneumatic system as we see. To test the Lindeberg system, low voltage alternating current is sent through elements to the outer cases. This current heats the cases until the discrete material releases enough gas to close the contact diaphragm, and the initiate fire warning will illuminate. When the test switch is released, the sensing elements will cool, allowing the discrete material to reabsorb the gas. Once absorbed, the contact in the diaphragm switch will open and the fire warning will stop.